Hello everyone, my name is Dr. Kravchenko Ekaterina, and I'm very happy to present our work on transforming construction waste into resources for 3D printed concrete. This research is a result of a wonderful collaboration, and I'm happy to present my colleagues, Dr. Mohammed Huzaifa Raza from the University of Hong Kong, Dr. Svetlana Besklubova from the University of Cambridge, and Dr. Georgy Lazorenko from Novosibirsk State University. In this presentation, I will present four main parts: the background and motivation of our research, the methodology we use, the key results we obtained, and finally our conclusions. The construction industry is responsible for a significant amount of global carbon dioxide emissions, resource and environmental damage and degradation. Traditional concrete relies heavily on natural resources like sand and cement, both of which have high ecological costs. In this work, we explore how waste concrete materials, specifically recycled fine aggregates and industrial byproducts like fly ash and blast slag, GGBS slag, can be transformed into valuable resources for 3D printed construction. We evaluate both the technical performance and sustainability impacts of these materials, including a detailed life cycle assessment comparing 3D printed structures with traditional casting. Our goal is to offer a more sustainable and economically evaluable pathway for the future of construction. And now let's go to our methodology. The methodology consists of several key stages. We started with a comprehensive literature review with three steps: 3D printing in geopolymers, 3D printing with recycled aggregates, and the incorporation of waste concrete into 3D printed materials. Based on insights from the literature review and based on the results of our preliminary laboratory testing, we developed a mixed design. We prepared four different samples, two for 3D printing, one with natural fine aggregate, and another one with recycled fine aggregate, and also two samples for casting with natural and recycled fine aggregates. Next, we evaluated the fresh properties of each mixture to assess printability and workability. After that, we conducted compressive strength tests on the 7th day of the carbonation curing. These tests were performed in three orientations, XYZ, to reflect the anisotropy behavior of 3D printed concrete, and it was in accordance with standard procedure. Finally, we carried out a life cycle assessment to compare the environmental impacts of 3D printed concrete with traditional casting. And the life cycle assessment focused on three key categories: damage to ecosystem, to natural resources, to human health. In our life cycle assessment, we examined a realistic case study of a standard concrete wall constructed using both 3D printing and traditional casting methods. We considered not only the materials but also the energy consumption, equipment, and time requirements for each stage of the construction process. For 3D printing, we accounted for the energy during mixing, printing, and infill, as well as the time needed for material preparation and extrusion. In the casting process, we included the use of formwork, mixing operation, and pumping, along with the energy associated with each step. We observed that the recycled aggregate mixture for casting had the lowest slump due to the irregular shape of the recycled particles. So for 3D printing, this mixture was initially too stiff to pump, so we added a small amount of sucrose to improve its flowability. Recycled mixture showed better dimensional control, which was confirmed through real-time printing trials. Overall, all mixture with recycled fine aggregates showed better stability and dimensional accuracy, which are key for successful 3D printing. We evaluated the 7-day compressive strength. As expected, the cast samples with recycled aggregates showed the higher strengths overall due to better compactation and a more monolithic structure. And the 3D printed sample shows slowly lower strengths, especially in the lateral direction due to the layered structure and presence of interfacial voids. So strengths varied depending on the loading direction, with the highest values recorded along the printing path. Recycled aggregates performed well in both methods, demonstrating their strong potential for structural application in 3D printed construction. In our case study, we found that the use of recycled aggregates reduced global warming potential by over 6% in 3D printing and about 4.5% in casting. Among the two methods, 3D printed consequently showed lower global warming potential, primarily because it avoids the use of plywood formwork, which added nearly 20% extra emissions in the casting process. We also observed that sodium hydroxide and steel reinforcement were the main sources of environmental impact due to their energy-intensive production process. Overall, 3D printing with recycled materials not only performs well technically, but also significantly reduces environmental impact, especially in terms of global warming, acidification, and ozone layer depletion. To evaluate the overall sustainability of each material and method, we used the overall performance index, like rank. This index combines and normalizes all impact categories across ecosystems, resources, and human health dimensions. In our study, all categories were equally weighted, and the results show that the 3D printed wall using recycled materials had the lowest overall environmental impact and ranked as a first. Compared to casting, 3D printing reduced the total environmental impact by nearly 30%, and the use of recycled aggregates contributed an additional 6% improvement. Our sensitivity analysis focused on the reusability of plywood formwork in the casting process. While materials like sodium hydroxide and steel cannot easily be reduced without compromising strength, formwork can potentially be reused, depending on the quality of the material and the complexity of the building design. The results show that reusing formwork even once can significantly lower environmental impact. However, when we use it 10 times, for example, the overall impact of casting still remains higher than 3D printing, which requires no formwork at all. So this demonstrates that 3D printing is not only more efficient, but also less sensitive to design complexity, making it a scalable solution for sustainable construction. We demonstrated that with small adjustments like lowering the water-to-binder ratio for natural resources and adding a small amount of sucrose for recycled ones, both printability and buildability could be achieved. Mixture with recycled fine aggregates showed higher compressive strengths than those with natural ones, especially in casting. In 3D printing, strength was slightly lower due to the use of sucrose, but still within acceptable limits. Our life cycle assessment showed that 3D printed walls using recycled aggregates had significantly lower environmental impact, primarily because they eliminate the need for plywood formwork. Even through reusing formwork in casting can reduce impact, the 3D printing process still remains more sustainable overall. These benefits will only grow stronger with the use of renewable energy and industrial scale adaptation. Thank you very much for your listening and for your attention. If you have any question, please write email or message me. Thank you very much for your attention. See you.